Thanks all of you for being here. I'm really excited to teach this class. As Andrew mentioned in the introduction, I teach a semester-long graduate version of this. This is also, I think, the third time I've done this for Statistical Horizons. So it's probably the class that I've taught more than any. And that's good because I really like this topic. I think it's really interesting. As you all know, probably because you're here. If you look through many social or health science data sets, there's not a lot of continuous variables, right? And so the sort of basics we learned with linear regression are really useful, but limited in their scope and what we can do with them. Really, most of the data that we use is categorical in nature. And so this class alone can sort of take what you know, but just build on it, but expand your toolkit in a really huge range of ways. So it's a really useful, I think, really fun, really interesting topic. So what I want to do is actually start with about a 15-minute sort of big picture overview of what we're doing here with a couple of kind of fun examples. And then I'll pause and I'll sort of go over the logistics of the class, where you can get all the materials, the structure, the assignments, stuff like that. But I kind of feel like that's starting with syllabus day, which is, always kind of anticlimactic. So let's start with a 15-minute sort of overview, and then I'll pause and I'll tell you where you can get all the materials and stuff. Okay. So first of all, this is important to get on the same page. Just what do I mean when I'm talking about categorical data? And what do I mean specifically with categorical data analysis? So actually, I should probably start with the second half of this, right, is variables that are not continuous. So I'm putting the continuous variables, interval ratio variables, in sort of their own little bucket, okay? And then I'm saying basically everything else is categorical. What is this usually? We think of binary, right? Sort of like maybe a health example you could think of, does someone have the disease or not? Ordinal are perhaps the most common in social science data. So we ask like opinion questions or survey questions, and they're often of the like strongly disagree, agree, strongly agree nature. Those are really ordinal. They have an order to them, but they're not truly continuous, et cetera. I'll talk about all of these examples more. And so those are just at the variable level, right? But then categorical data analysis is really about when we have one of these categorical variables, but they're on the dependent variable side of the model. Right. So what I'm referring to now, right, is just the analysis of dependent variables that are not continuous. These are often, the term categorical data analysis is kind of taken off as the most common way to refer to this. You might see in older context, sort of limited dependent variables. That language is just a synonym. It's the same thing. So a couple of fun examples, and then I'll move to the more sort of research-based examples. Let's start with the one in the bottom right. So this was from 538, who covers elections and especially does predictions for elections. And this is the model that they built to predict the 2020 election. And this was their last prediction the day before the election. And so you can see they're trying to predict a binary outcome, right? Does Biden or Trump win the election? And they have an 89% chance. So they say if 100 elections were run, about 89 of them Biden would win and 10 Trump would win. Okay, so that's the way they're doing it. It's kind of an interesting presentation too of how they've done this with the dots to show really what is a predicted probability, which we'll talk about an hour. There's an 89% chance Biden's going to win. If you look at this one over here, this is from my Netflix account. And they're saying there's a 93% chance that based on what I've watched, what I like, that I would like this show, which I hadn't yet watched at the time. Indeed, I did watch it. It was very funny. And so they sort of nailed that one for me that actually, yeah, based on what I was liking. But what is this? This is actually a model, okay? The dependent variable, the outcome is, does Netflix think I will like this show? And then all the variables in the model, the independent variables, are other stuff I've watched, other stuff I've liked, et cetera. The last example here at the top is this is from a couple of years ago in my fantasy football team. And you can see they say that they think I have an 84% chance of winning the game at that time, which is kind of interesting because I'm actually scoring less points at the time than my opponent. But they're saying based on everything, they have information about all the players and the games to remain and whatnot. And so it's a continuously updating chance of who's going to win. Now, all of these are actually categorical data analysis. I can tell you all of these are actually binary logit models. That's what's actually happening behind the scenes. I'm going to teach you what they're actually using to get all of these predictions. But these are very sort of slick ways where you don't have to sort of know what's going on behind the scenes to get a sense that, like, oh yeah, they really think you're going to like that movie. Another really common one we see all the time. I do this, right? Whenever I'm thinking of buying something, whatever website I'm on, Amazon or something, I always look at the ratings, right? I say, what have other people seen? Well, this is could be kind of continuous, but really ordinal. There's really 5 options, right? You pick how many stars you would rate the thing on 1 to 5. 32 people have rated this. And you can see it's averaging out to about 4.5 out of 5, which would mean most people who've bought this really liked it. This would be one I would buy. This is incidentally the book I'd probably most recommend if you want some extra reading on this topic. The one at the bottom, this is if you've been to the doctor recently for an injury or something, you might have seen this. This is actually a real scale that's commonly used, right? The Wong-Baker Faces pain rating scale. And so it'd say, where would you rate your pain currently on a scale from doesn't hurt at all to it hurts terribly, it hurts the worst, right? This is clearly ordinal. This little face here is not twice as much, even though it's in the 4th position, that's in the 2nd. We don't really think this is twice as much pain as that. Really what we're just interested in are the information there. It's just that they're different left to right. They are ordered in that you're saying you have more pain as you go to the right. So those are some sort of fun examples. Let me show some examples in social, the type of data that health and social scientists use. So probably all of you should be at least a little bit familiar with linear regression. All of us probably have went through a graduate program in the health or social sciences or similar. And basically always there's a required class in either ANOVA or linear regression. ANOVA and linear regression are basically the same thing. But most programs don't require anything else beyond that. And as I mentioned at the very start, I think that's a really unfortunate because even though linear regression, again, is the building block that we're going to use throughout this seminar, it's super limited in what you can do. There's just not a lot of variables I'm interested in that are linear. Most of the ones, I think, are actually categorical in nature. So just a couple ones you could think of. Of course, this one was a huge one in the last few years. Right? Is it a vaccine effective at preventing disease? Well, the outcome is, well, the independent variable is, does someone get the vaccine or a placebo or not, for example? And then the dependent variable is a binary. Did they contract COVID, for example? Was it severe? Did they die, et cetera? The 538 example of elections, we could think outside of the US context when it's usually binary. It's almost always a Democrat or Republican that will win. Think about most countries, there's lots of parties, right? And so that's fine. We could have 6 unordered, just different parties, and we could still predict who we think is going to win. We could think this is important to a lot of us, right? How many publications does it take to receive tenure? Publications is a count, or tenure is a binary, you get it or not. How many drinks does someone have usually per week? The way we ask that too is often ordinal. It's often like none or 1 or 2 or 1 a day, et cetera. It's not often usually the exact number. We can think about comparing across groups. So here we might have categorical variables on both sides for this last example, right? Race ethnicity would be a nominal independent variable. Health we usually measure, especially the overall one, is like a 5-category ordinal. How's your health overall from poor to very good? So there we're predicting categorical variables with categorical variables. So we need the type of stuff we're going to talk about in the next few days. A couple brief examples. The General Social Survey, if you're not familiar with it, is a national representative survey of the US. It's done every 2 years, started in the early 70s. And it's about the just opinions of people in the US on social issues. And if you've ever looked through this data, nothing is continuous. Like there's literally nothing that's continuous in the US. They ask everything in these kind of wonky, weird, nominal and ordinal ways, right? What about the courts in this area? Do you think they're harsh or not harsh enough for dealing with criminals? Okay, this is clearly probably a nominal here, right? Because how could I order these? I could maybe order them from not harsh enough to about right to 2. All right, so I could maybe sort of order them, but really it's sort of 3 categories that It's not exactly clear. This is a clear ordinal, right? How often do you pray? But again, they're not like, what is several times a day? What number do I put on several? Well, I can't really put a number on it. It's just, it's more than once a day, but we don't really have more specific information than that. I mentioned briefly the sort of vaccine examples. This is an example of efficacy of various vaccines. All of these are binary. So they're different vaccines, different clinical trials, et cetera. But just saying how effective are each one, right? And so you can see the flu vaccine is always one of the least efficacious. You can see the coronavirus one against the original variant was quite efficacious, et cetera. But these are things, of course, that are extremely important, but you need categorical models for. Here's another example. This was, I believe this is from the New York Times. They, during the pandemic, had sort of a running updated way to display the COVID statistics. This is how they were doing severity. Oh, actually, this is from my university. The next example is from the New York Times. So these were actually the cases at my university where I'm at, Purdue. And so they would see the employees who got COVID, the students, what was the severity of the case that they had, from completely asymptomatic to a severe case, which they were using, and they were real-time updating it to sort of make decisions about in-person classes, masking, et cetera. So this example is the one that's from the New York Times. So this is actually something we haven't looked at yet, which is a count variable. So when we report cases by day, we sort of think of it as it's kind of continuous because they're big numbers, there's a zero, but really it's a series of binaries added up. So basically think of everyone in the country could currently have COVID or could not have COVID. So every single person is a 0, 1, right? So each person has it or does not, and we add all those together, and then we get the count of the number of cases in a given day. Or you could think COVID patients in a hospital. Again, it sort of seems continuous, but actually these have really special properties. They have really wonky distributions that make them not amenable to using a continuous, like a linear regression model. So they're kind of they're the closest to continuous that we're going to work with, but they're like I said, they're special. They actually have some tricky properties, but we'll talk about how to deal with them. Okay, so I call this class categorical data analysis because, yeah, we're trying to learn how to analyze dependent categorical variables. Sometimes when I teach it, I have a subtitle to the class, which is, handling nonlinear interaction or nonlinear effects. Why? Because really what makes categorical models a little bit tricky, but also really flexible and really interesting is because they produce nonlinear effects. So what do I mean by this? Well, so a linear effect is one that is a straight line. Okay, so it's straight, it's linear, and also it doesn't matter across other variables. There's no interaction effects, basically, is what I'm saying here. So in linear regression, we have models that are sometimes nonlinear or effects, right? And so what I mean is it's a straight line by default in linear regression, but we probably have learned putting like h and h squared in a model where, okay, now it's a curve. So actually even a linear model isn't always linear in the effects. And then we can think about interactions too. So you can think about, you have an age slope, but maybe you put a binary measure of sort of gender in there or something, and you let the slope differ for men and for women. Okay. Well, then you're letting it be interactive. So by default, right, you would just have sort of parallel lines for your groups. If you had, let's say, 3 groups, you had men, women, non-binary individuals, right? Well, you've got this parallel. Well, we know we can be flexible in linear models and make them interactive, but by default, they're not. The thing that makes categorical dependent variable models is that the models are always nonlinear and always interactive. So actually, you don't have this choice that you have in linear, where, right, you can force things to be straight lines, or you can let them, be squiggly. You can let things interact. You can let, the slope differ by genders. You don't have that choice. Categorical models are nonlinear and they're interactive. Now, this makes them, again, quite flexible and really interesting and actually more accurate, sort of nuanced ways to understand the social world and your data, but it also makes things more complicated, right? Things are really simple when it's a straight line and they're just intercept shifts for groups. So we're going to have to start to think about, for example, what value of an independent variable do we care about? Let's say age. Age is the predictor that we care about. Well, we're not going to have one effective age. You're not going to see the effective age is to give a 2-unit increase to whatever thing you're studying. No, it's going to be a different effect for 20-year-olds than 50-year-olds, which is going to be different effects than for 70-year-olds. Okay, we just have to accept that that's going to be a complication we have to deal with, but also any possible thing you could study. So just think about whatever the topic is interesting to you and think about age. I guarantee you the effect is not the same for 20-year-olds as for 70-year-olds. Right? It's just like implausible in almost any case that would be true. So again, it's a complication, but it's a sort of complication that's going to allow us to, I think, do some interesting things and do some more realistic things. We also need to think about how big are the effects we should think about. Are we interested in a 1-year increase in age, a 10-year increase in age, a 20-year increase in age? We need to think about that because it's going to make a difference now. We're also going to be think about what we're doing with the other variables in our model. So what about gender? Do you need to make separate predictions for the different gender categories in your data? Because the effective age is going to differ across the different categories of other variables. So what I have down here at the bottom is the sort of important point, is that when you have a linear model where everything's linear, really what you do is you estimate the model, you get your nice coefficients, your p-values, and you're kind of done. I mean, you need to interpret them and everything, but like you don't need to do anything else. You sort of have all the information you need. That's no longer the case. Actually, those coefficients aren't going to be very interesting or very useful now. You're going to need to do something to follow up. Okay, because again, age is going to have a different effect for different ages. And so you're going to need to think about where to look at it. It's going to have a different effect across different groups. So you need to think about which groups are interesting. The good news is, even though it's a complication, we have really, really good tools to do. And again, it's going to give us a more realistic, I think, interesting description of what's going on. So it's a complication worth learning because the payoffs are really good. Let me read a couple of quotes that I think are really good, and that will sort of serve as a bit of a guide for the way I teach this. So this is from Scott Long, who wrote a couple of the really great books on categorical data analysis. He says, unfortunately, all too often when these models are used, and he's referring to categorical models, the substantive meaning of the parameter, the coefficient, is mainly what he's thinking about, is incompletely explained, incorrectly explained, or simply ignored. Sometimes only the statistical significance or possibly the sign is mentioned. So what does he mean? People estimate their binary logit model. They're predicting, does someone have this health condition or not? And he said, well, what do they usually do? They say, well, it's a positive effect and it's significant. Or they say it's null. Or they say it's a negative effect and it's significant. And he's trying to make the point. That's who wants to know, like, yeah, age is positively correlated with that health condition. As you get older, you're more likely to have that health condition. I mean, like, yeah, duh. That's true of most every health condition, right? But like, what does that mean substantively? How big is the effect? How likely am I going to have that? You really need to do something to go further to really understand the substantive meaning of what we're doing. So that's what we're going to learn. How much has that changed? Scott was writing in 1997. For this one, well, let's see an overview from 2021. So they said they were overviewing the type of interpretations that people did in published work with categorical models. Okay, so this is a very empirical. They're actually looking at what people are doing as of 2021. And they found several different interpretation techniques were applied. The most common strategy was to simply look at the p-values and the sign of the coefficient to infer the direction of the effect, ignoring both the strength and the form of the relationship. So sadly, in the ensuing years since Scott wrote that in 1997, not that much has changed. Most people are doing very unsatisfying, unmeaningful ways to interpret these models. And there's really no reason for that anymore. When Scott was writing in 1997, it was really hard to do this stuff and the software had not caught up and to do it. It's really not very hard now. And it's really way more interesting, way more satisfying, way more useful to go beyond the sign and significance. So that's what we're going to try to do, right? There's a lot of really interesting complexities in these models. But we're not going to see them as nuisances. We're going to see them as opportunities to really learn something interesting about the world. Okay, so I keep referring to, this is going to make things more complicated. It's going to be a little bit more difficult. What do I actually mean by that? So let me show you exactly what I mean. This is a linear model. This would be a linear regression model where I've got two variables in the model. I've got x, which is this nice continuous variable. Okay, it goes from 0 to 5. And then I've got d, which is a dummy or a binary variable. So again, this could be age and any sort of grouping that you're interested in. Let's say this is age, and this is if your parents went to college or your parents didn't go to college, something like that, right? Well, really only we need is two numbers to explain everything that's going on here. Basically, we need beta. What is beta? Well, that's the coefficient on x, the continuous variable. That's just simply the slope. Why do I only need one number? Because it doesn't matter if you're going from 1 to 2. That's the same exact effect as going from 3 to 4. Now, it also doesn't matter which group you're in. So, right, let's say, again, this was maybe your parents went to college, okay? And this is your parents didn't go to college. Well, it doesn't matter. The size of beta is the exact same, regardless of where on x and regardless of which group you're in. So I need one number for beta, right? That's the effect of aging. This is, let's say it's a developmental process because we're studying, let's say, 0 to 5-year-olds. Similarly, to understand what's going on in the groups, all I need to estimate is gamma. It's this gap between the lines here. That would just be the coefficient. So it's just an intercept shift between the groups. What's the effect of the grouping? Well, it's this much difference between the groups. Again, it doesn't matter if they're 1-year-olds or 3-year-olds or 5-year-olds. It does not matter. The grouping is the same. So this is why linear's effects are really easy, right? And you really need the graph helps, of course. I always recommend making the graph, but you don't have to have the graph, right? Like you really just need these two numbers, what is beta and what is gamma. I would also say this is really boring and that there's nothing in the world that looks like this, right? There's like nothing where age has a completely straight linear effect, and there's basically nothing where there's like nothing going on with the groups different ages. Like, is it really plausible in any developmental process that groups stay identically separate across the spectrum as opposed to no? I mean, like they're starting to go to elementary school here or kindergarten, and things are going to change in interesting ways. So this is an inherently nonlinear model. This is actually a binary logit. If you haven't seen it yet, that's what this seminar is about. So just hold on for 15 minutes and we'll get to this. But this is what we would use for a binary dependent variable. Now, one thing I want to show you is that I've estimated a single beta and a single gamma. In other words, I've estimated a single coefficient for x and a single coefficient for d. So there's no h squared, x squared in the model, and there's no interaction effects. That's important, right? There's just one coefficient for x, one coefficient for d. Despite that, right, despite no explicit nonlinearities in the model, no explicit interactions in the model is indeed nonlinear and interactive. Okay, what do I mean by that? If we just go left to right on the x variable, where you can see the effects are pretty small here, and the effects are pretty big in the middle, and they get small again. So if I go to this dashed line, it's easier to see. This is the effect of going from 1 to 2. It's this delta change. It's a really, really big change. But if I go from 3 to 4 on this dashed line, you can see it's a really small increase. And if you could see, if I go to 4 to 5, it's basically null. There's basically nothing going on. So it's nonlinear, despite the fact that we don't have sort of like squared terms or any other ways to intentionally make it nonlinear. The group difference also, you can see, varies in size. So if we look at the difference between the lines, you can see they're quite big here. They're getting a little smaller here. And you can see the difference between the lines is basically non-existent here. So imagine this was, again, kids whose parents have college degrees or not, you're some measure of sort of social class you're interested in. Well, here we would see there's a big difference between the kids, but that gap between the kids actually shrinks by the time they're like at school age. Just really interesting, right? It's really interesting that there's a big gap between the groups, but the groups actually at some point become more similar. Right? If you found this in your data, it's actually interesting. But it's going to make things harder because the deltas, so the capital deltas, the sort of triangles here, are different in size depending where we're looking. The lowercase deltas, which is the effective x, right, are different in size depending on where you're looking. They're also different in size depending on which group you're looking at. So quickly look at delta 3 and delta 4, zone in on those. So that's now the effective x. It's the effective aging from 3 to 4. But you can see it's way bigger for this group than it is for this group. So that's another side of the interaction effect we'll talk about. So more complicated, lots more stuff you could look at, right? As opposed to, if I go back really quick, a single beta, right? Because I have 4 on here, but they're all the same number, a single gamma. Here we've got what, 1, 2, 3, 4, 5, 6, at least 6 things we've calculated, and they're all different. Each number is different. So part of it is which ones do I use? How do I summarize? We'll talk about all that stuff. Okay, so what we're going to cover, there are extensions to these things that you're welcome to ask me about, but we're going to cover the sort of most commonly used models to make sure I give you the toolkit of the things that most people use. But again, there are some interesting extensions. If you're thinking about using, feel free to ask at a later point. We'll talk about modeling binary outcomes. We'll talk about modeling nominal outcomes. We'll talk about modeling ordinal outcomes, and then also counts. And as you can see, there are multiple models people use within each one, and I'll at that time tell you about pros and cons of each. We're talking about a lot of ways to interpret the models. We'll tell you what the coefficients do. They're something. They're not the most useful, but they're there. Talk about how to make predictions. Predictions are really graphs. So if I go back really quick, this is a graph of predictions. It's what I would predict at various levels of x at various levels of d. We'll talk about how to make graphs like this. Talk about marginal effects. Again, if I go back really quick, all of these deltas are actually what we call a marginal effect. When we have effects that are different at different values, we really need a different method of interpretation. So I'll teach you how to do that. And then lots of ways to graph all the above. We'll also talk about some complications. Talk a little bit about how to think about significance for substance. Really, a lot of what I'm doing is trying to give you tools to really understand what's going on in your data and to sort of move beyond like it's significant or not. Talk about mediation. If you think there's sort of a process that, well, this thing matters, but it matters because it affects other things, it affects mechanisms or mediating variables. We'll talk about how to do that. It's a little tricky in these models, but lots of good solutions exist. We'll talk about how do we think about interaction effects? How do we think about the effect of one variable varying on the other, which is actually complicated here because the models are already interactive, but we can make them even more interactive. And so it's just something worth thinking about. How do you wrap your head around interaction in a model that's interactive? And then we'll talk generally about when I have multiple models, I want to know whether something's equally effective across different outcomes, et cetera. How do we think about comparing across? So that's where we're going. We'll cover all of that in the next few days. Some extensions that I don't cover here, but I wanted to at least mention them first of all, because once you've taken this class, you might be interested in doing a follow-up and you'll have the tools you need to learn this. Or you might just want to ask me about it later on. So I won't cover them here, but let me mention some of the things that what we learn in the next 4 days are building blocks that you need and that have some really cool stuff you can do once you have this in the back. The first is anything we cover in this class, literally anything, has a sort of sister model that is multi-level in nature or that's longitudinal in nature. So, right, you've got kids nested in classrooms, nested in schools. Well, you need a multi-level model for that. But it's fine if it's a nominal dependent variable. That's fine. You have a longitudinal model. You've followed people over several years of their life. Again, it's fine if you have a binary dependent variable. You could absolutely build in the longitudinal aspect on top of this, but you need to know the categorical part, right? But we can extend all the models we're talking about to these contexts. There's some other types of ones that are specifically about sort of not quite continuous, but kind of close dependent variables. Percentages and proportions they look pretty continuous, but they have these bounds. So, right, a percentage can't go below 0 or above 100. And so they have some special properties because of those bounds. They're not truly continuous. You don't want to use linear regression for those. There are also censored distributions where maybe you have a floor, and so you can't go below a certain number, but you can go as high as you want. Again, they're close to continuous, but they actually have some tricky properties because of those floors and ceilings. Machine learning, extremely popular right now. Most machine learning tasks, not all, but the vast majority of them, are really 0-1 prediction tasks. It's really, how do I build, using lots of data, the best prediction of whether this thing or that thing is going to happen. If you think back to like the Netflix example I gave of, do they think I'm going to like the show or not? Really, they're using machine learning techniques. They're using tons and tons of data on tons and tons of people to just predict 0-1. Will this person like this show? Yes or no? But really what's happening is these are logits. So if you heard of lasso random forest example, they're really just sort of building on some interesting new tools into just the binary models we're going to learn here. I think they're really cool, by the way, and can do some useful stuff. But again, under the hood, really at their base, they're just binary models. I teach a whole class on latent variable models. There's also a ton of really good statistical horizons seminars on these. And so first of all, when we have, so latent variable models, have a concept that I think underlies a bunch of different individual items. So let's say I'm trying to measure depression. We usually don't ask someone, do you have depression or not? Because some people haven't been diagnosed. People have various ranges of it. So like even people who say they're depressed, right? There's a huge range in where they're at. And so usually we ask like 10 questions or something that are 10 different depressive symptoms. But what we're trying to get at is depression. And the individual items are really symptoms. Well, what if those are asked as binary? Did you have the symptom last week? Yes or no? Ordinal. Did you have the symptom from never to once to a few times to every day, etc.? Well, really, these are just categorical models because you need some way to deal with these items that are categorical in nature. So we could do things like item response theory, nonlinear factor analysis. Sometimes the latent variable itself is nominal. So let's stick with the depression example. You can think of depression going from a like absolutely none to extremely depressed, and then there's variation all between. We could also think of categories. You could think of like not depressed, depressed but not severely depressed or something. So we can think of it as like nominal. Well, that's clearly some categorical stuff going on. But again, these are just using the tools we're using here, but extending them to this case of a latent variable. The final thing, and there are more than this, but just I wanted to pick some really popular ones, is if you're interested in networks, these are basically all binary predictions. They're usually predicting things like, does a tie exist? So let's say we have a school context and we have friendship networks. Well, we're saying, okay, pick number one, pick Trent. Well, is he friends with that person? Yes or no? Is he friends with that person? Yes or no? You can see they're all really just binary predictions. Like, does that tie exist? Does that friendship exist? So they're pretty straightforward extensions of the stuff. Okay, here's how I've organized it. Just a second, I'm going to talk about some of the logistics, and then we'll get straight into binary. I see a question in the chat really quick. Do I teach all of these different methods? Not here. So these I don't teach in this class, but you will learn the building blocks you need to then use these. But these I don't teach in this class, but if you're interested in any of these, feel free to ask, and I'm happy to recommend a seminar or recommend a book or stuff like that. And then you'll see we'll go to nominal and ordinal tomorrow. We'll do counts and zero-inflated, which are special types of counts. And then we'll go on to sort of complications that cross-cut all types of models, interactions, comparing across models, etc. Okay, so the first thing to note is there are assignments, but they are optional. So right, you're not getting a grade in this class. It's really up to, or the seminar, right? It's really up to how much time you have to devote right now and how much interest you have in these various ones. But I want to give you assignments that I think are really useful for learning this stuff if you have time. But you can, of course, do them later if you don't have time. during these, or during the class days. So at the end of the first 3 days, there is an applied assignment. What this is using real data. It's nice, clean, beautiful data that I've cleaned for you, so you don't have to spend your time with that. Saying here's a template analysis. So for day one, it's a binary dependent variable model, and you've got 5 or 6 predictors. And I walk you through in about 10 steps. Here's exactly how I would approach doing this analysis, step by step. Here are the various ways to interpret it. Here's the various graphs you can make. Here's the ways you can check the model, all that stuff. So it's a way both to make sure that you can actually apply the sort of hypothetical stuff we're doing in class to real data, get hands-on. And then I also give you template code. So if you're familiar with Stata or R, you can also see the exact code you would need to do that. And so you can make sure you can translate from the theory we're using to the actual application. There are 3 files for each assignment. And let me show you what they are, and then I'll show you what it looks like. The first one is the assignment without any answers. So it's just the questions you need to answer. There's template code that goes along, and it's all nicely ordered. So, question 3, there's a nice section in the do file, and I'm saying question 3, so you can see the code that goes with it. And then there's also an assignment key that has all the answers. So basically, this is sort of choose your own adventure. Here's how I would think to do this. If you have the time and the interest, try the assignment without opening the key. Get as much as you can. Look at my example code, right? Try to do as much as you can. And then once you've got as far as you can, then go read the answer key and see how well you've done. And I'll tell you in a second a way you can ask me questions if you're not sure why you got something wrong. Or if you don't have quite that much time, maybe you have 15 to 30 minutes to devote to this, just read the assignment key with the answers. So, right, you don't have time to really implement it yourself, but you have 15 or 30 minutes at the end of the day to read through what I've done and see how I would do this and how I would interpret it, and just see if everything makes sense to you, or again, are there questions or there things you're not really sure with. Again, I'll tell you in a second about a way you can ask questions when we're not in class. The other thing that I will do is that at the beginning of the next 3 days, I'll spend like 15 to 20 minutes at the very beginning going over the assignment, just sort of saying, here's what I did, and then taking any questions you have then too. All right. I see a quick question in the chat, which is there a package in R to calculate the marginal effect for ordinal models? Yes, absolutely. So actually day 2's assignment is about ordinal models. And so there is both a Stata and an R template. So yeah, there are really good ways to do that in either Stata or R. Let me actually answer that in an even more generic sense because it's more helpful. There are ways to do absolutely anything I teach in this class in Stata or R. And I have example files for basically all of this, both in Stata and R, that I'll show you in just a second. Okay, so asking questions. So these lectures are recorded, and so you'll get a link, and so you can go back and rewatch anything you need, or if there's something you need to dip out for 30 minutes or miss something, you'll get the link. Usually it only takes about an hour after we're done for the recording to process, and then you'll get that. So one of the things you're really getting is it's a lot easier to pay attention if you're joining live, as we all know. But the other thing is you can ask me questions in real time, right? So as we're going through slides, you don't have to wait to ask me as you go. I've taught quite a few of these at this point. People seem to like the Zoom chat, I think, because you can sort of edit your thoughts and you can enter your question at any point. And so the nice thing is you can ask a question in the chat. I'll finish my point. You're not going to interrupt me. Once I come to a nice stopping place of what I was explaining, I'll read the question and I'll answer it. Having said that, some questions are hard or they're going to take longer. They're hard to type. So absolutely, you could use the raise your hand feature so I can see you. You can unmute yourself. You can ask questions that way too. Completely fine. But again, just from having taught these, people seem to like the quick clarification questions in the chat. And then maybe if you have a really long, involved question, you could unraise. But I really don't have a preference. I'm happy to take questions either way. Okay, what about questions after you've had time to process this? As you're thinking, you're having dinner, and you're like, wait, I didn't actually understand that thing we were talking about. What about as you're doing the assignment and you come to something in R and Stata or it's data that you don't really understand? What about questions about what you're doing? These are the ones that I think people sometimes feel like self-conscious about asking, but are kind of the most fun for me. Presumably, you're taking the seminar because you're going to need these methods for something you're doing. Great. Tell me what you're doing. Tell me what the questions you have about it are. That's super fun for me to hear how you're using this and to help you with that. So not only are you getting sort of me teaching you this stuff in the next 4 days, you're also sort of getting me as a bit of a consultant to help you think through the research questions you have. So please do ask me that stuff. Or just if you want suggestions for further stuff, I've got tons of materials and stuff that I could give you on top of what I have time for. So we use Slack for this. Let me put the link. So this would have come in an email to you earlier, but let me also go ahead and put it in the chat right now. So we use Slack for this. You all will have been given access to it. So this is from last time I taught it, but when you go into Slack, Slack's really great. You can just post your message and you can ask me, I don't understand this. The thing that's really cool about Slack is you can use, you can attach things. Like if I look really quick, and this is from the last time I taught it, right? This student not only asked me a question, but they attached a little screenshot of, hey, why are the numbers different than what I was expecting? You can link to stuff. I can add, I can send you a reading. I can send you stuff. It's really nice. It also works really well for code. If you look over here on the right, someone asked me a question of how to do things. And not only did I explain it, me writing, but I also posted the exact code you would use. So Slack's really good for this type of stuff, I think. And the nice thing is I'll check Slack sometime late tonight, sometime tomorrow morning. So I'll check it a couple times between classes. And I'll answer any question you have. Again, this is where you can ask stuff about the assignments, but you can ask anything. Like really feel free to say, this is not exactly what you taught in class, but I have a question. I might say I don't know the answer, but if I know the answer or I know a resource to point you to, I'm more than happy to. So use Slack as a resource to really get the things you're interested in. The second thing is there's a Dropbox folder. Let me also put that in the chat. And the Dropbox folder has, let me see. Okay, there we go. The Dropbox folder has all the materials for the class. So first of all, it has these slides. They're PDFs, but the slides that I'm using right now. It's also got some instructions for how to set up Stata or R. Anything I show in these notes has replication files. The replication files are a little more complicated, so let me explain that in a second. But literally anything you see in these notes, any graph, any output you see, all of the code and the data to replicate it, you have. Okay, so absolutely anything. There's a graph on slide 500 that you're interested in. There's code to reproduce the graph on slide 500 that you have. But again, they're like 700 slides, and so there's a lot. It's a little overwhelming. Okay. And so what I did is I also give you template analysis files. These are really simplified, cleaned up, annotated with a lot of comments and suggestions files that follow the different type of models. So let's say ordinal models. Okay, there is a file that is a template analysis of an ordinal model. So it's just the 100 lines of code that are like the most important things you really need to know. So that's what I mentioned. For any type of model we do, I've got Stata and R templates that are in sort of streamlined, organized sort of keys you need. There are also just a lot of readings and examples that I refer to during this that are absolutely not required. I actually don't expect you to really have the time or bandwidth to do them while we're during the course, but they're things I refer to, I want to give to you. They're all up there as PDFs. This is also something like a live Dropbox folder, which is why I like you to bookmark it instead of downloading everything now and never looking at it again. Because as people ask me questions during class or on Slack, I'll actually add to it. Right. So if I've got some example code or I've got a reading, I won't just give it to the person that asked the question. I'll put it in the Dropbox folder so everyone has access to it. So here, so a computing setup will teach you how to get Stata set up. All the assignments are here. So if you look, right, there's two lab 1 or the first assignments. The first one is the actual one. The second one is the answer key. If I expand this, you can actually read the whole title. So right, the binary dependent variable lab and the binary dependent variable answer key. You can see that the code for either R or Stata are in there. I mentioned the replication ones. Again, these are really long, really complicated, but I want you to have them. And then the template files, which are the sort of simplified, more streamlined templates for how to do any of these analyses. And the slides are right there at the beginning. Okay. See a good question in the chat about the format here. You probably won't know enough during the first break. So the way we're scheduled now is we go 10:30 to 12:30. I usually like to take a break right in the middle, like a coffee break. And then you have an hour-long lunch. And then we'll go from 1:30 to 3. You could probably get started on the assignment if you wanted during lunch, but I don't expect you to. I don't really expect you to do it until, at night between the sessions, especially because I don't have time. But if you want to get started, you could probably do half the assignment by the time we get to lunch. But I'm really thinking most people will work on them sort of tonight, ask me questions in Slack. I'll answer them in Slack, and then I'll also go over questions tomorrow morning. Awesome. A couple of recommended books. These are more statsy. Let me go full screen again. These are sort of more statsy, but they're really important. They're both really good. So if you want really the background of what's actually going on beyond under the hood, both these are very good. Most people, just from experience teaching this type of thing, are a little bit more interested in the sort of applied aspect of it. So yeah, you're interested in knowing the statistics and math enough to do it, but you really want to use this stuff. So these are more applied versions that I think, again, are for most people kind of what you would be interested in, where they cover the details of the model, but not in huge amount of detail. But there are a lot of like applications to data, a lot of code. The one on the left is what I would recommend if you're using Stata. The one on the right is what I would recommend if you're using for R, because it's really useful to have the examples in the book line up with the software you're using. I've read both of these. They're both very good. I should also say, you in no way need a book. Everything you really need, I'm going to give you in this seminar. I've given you all the code. I've given you all the slides, etc. This is just supplement. If you want even more, you'd like to see more examples, more detail. So these are not necessary to have, but they're useful. Okay, any questions about the class, about the logistics, before we get right into the fun stuff? I see a question. So yeah, feel free to chat or unmute yourself. Either one is fine with me.
Hi, Dr. Mize. Can you hear me? Oh,
yes,
sorry.
I can hear you, sir.
Thank you. I was wondering if we'll have the R script or R code to follow through with class as well. I know we're given it for the homeworks and supplemental materials. I was wondering if we have it for just following through the class. I know you will be using Stata primarily.
Yep. Yeah, great question. So what you have is, if you go into the template files, you have everything in R. So what we're going to talk about pretty much for the rest of today, maybe we'll get through with that, is binary. And so this template analysis is the closest corollary to everything we'll talk about today and how you do it in R. Now, this is the simplified version. It doesn't have absolutely everything, but it's pretty detailed, and it has everything you really need. So the sections of the course are lined up like this. They're binary, nominal, ordinal, count, interactions, testing, and fit. So you could absolutely sort of have this open as we're going through the class, if you wish. The only thing you don't have in R, you also have for the assignments. As I mentioned, you also have R code for the assignments. The only thing you don't have in R is you don't have the full replication of all 700 slides. And that's because I did it once in Stata. I don't think there's a point in doing it again in R. But does that fully answer your question, I hope?
Yes, thank you. I was looking at the lab assignments, but I didn't see the in-class exercises.
Awesome. Yeah, the template files are really the maybe the most useful thing I give you. And those are all mirrored in Stata and R. And they have more detail than the assignments too. Any other questions before we move on? Okay, awesome. If something comes up, again, we'll take a break here in maybe 10, 15 minutes. You can ask a question during the break. You could put something in Slack, right? You can also put stuff in Slack as we're going, if something comes to you. I won't read it until, after the class, but feel free if, you're thinking, ooh, I have this great question about my work. That's about something we're talking about. You could put it in Slack and I'll read it later and get to you tonight. Yeah, great question about if you're familiar with R, is it hard to switch to Stata? If you already know R or you already use Stata, I would stick with the one you know, because there's no real great reason to use one or the other for what we're studying. Both Stata and R are really flexible to do basically anything we're doing. So anyways, if you're already familiar with one, I'd probably just stick with it. If you're not familiar with either of them, you're coming with like a background in maybe SPSS or something, which or SAS, which really are more limited for using these. Stata is absolutely the one I would recommend going with, because Stata is so much easier to learn than R. It's much more user-friendly, much more easy to learn. So yeah, if you're new to both Stata and R, I'd really recommend Stata. But if you already know one or the other, I just stick with the one you know. Awesome. Okay, so let's talk about binary models. And again, I'll give like a little bit of a preview here, and then we'll take a coffee break in just a few minutes. But let's at least get this preview in before we do that. Okay, the first thing I want to talk about, I mentioned, right, like the subtitle of this class sometimes is about nonlinear effects. Okay, what do I mean exactly? I've shown you sort of the graphs. If depending on your background, you might have heard this differently. In physics, they use the word nonlinear to simply mean the outcome is not a product of all of the causes. So in other words, if you know 5 things that go into something, well, you simply add up the 5 things, and then that sum is what's going to happen. Really, they're sort of pooling nonlinearities, like, well, it's not the simple additive product because it's a not straight line, but they're also pooling over interaction effects, which is, well, it depends on which category you're in. That depends on how the other variable matters. So I usually separate these, and when I'm talking about nonlinearities, I'm really talking about something specific, and that's that the effect of a variable is not constant. So this would be a continuous variable, that's a linear effect, it's straight. If it's a curved effect, it doesn't have to be just a curve, right? It could squiggle in interesting ways. If it's just not a straight line, if it's not a constant effect, I'm referring to a nonlinearity. And then I'm going to separate out interaction effects. An interaction effect, which you might have heard called moderation, depending on your field, it's just when the effect of one variable is contingent on the effects of another. So for example, how does age work? Well, if it depends on your race ethnicity, then that's an interaction effect. I also want to mention, I'm talking about effects, not models. So I'm assuming knowledge of linear regression here, so I'm not teaching it to you, but actually all these complications we talk about, you can get in the linear regression model. So just because you have a linear model, don't think the effects are necessarily linear. Again, if you've ever put age or age squared in the model, you've got a non-linear linear regression model. So the key thing is the effects, not about the model itself. And as we'll talk about, when things are nonlinear and or interactive, well then really the coefficient is not that useful. We really need to go into predictions, other ways of doing this, which I'll teach you. I love this tweet. This is Neil deGrasse Tyson, the astrophysicist. This is in science, when human behavior enters the equation, things go nonlinear. That's why physics is easy and sociology is hard. As a sociologist, of course, especially love this quote. But right, Tyson is an astrophysicist. He's not dunking on the intelligence of physicists, right? He's really talking about this property is that, again, when they're using nonlinearity, they're talking about both nonlinear and interactive effects, or the combination. And yeah, there's some things in physics that it's like, if you push this thing this hard, it will move that much. And that's like a property of physics if you know the surface it's on, the environment, etc. Nothing in human behavior acts that way, right? Is people are weird and they make different decisions, or different outcomes in their life happen because of all the other things about them, because of their backgrounds, because of their characteristics, all this stuff. And as we mentioned, like the age effect, so nothing that affects you in your 20s affects you the same thing in your 70s. It's just different. So that's what he's referring to, is that humans are messy. We don't work as simple products of all of the causes. So it makes things more complicated, but it's really interesting too. Yes, I completely agree with Danielle. Yeah, I love this quote. I appreciate some appreciation that this stuff's hard. Okay, so why do I keep talking about these nonlinearities? Why am I talking about physicists talk about it? Whatever. It's because we're in the land. We're an hour into the seminar, and we are into the land where nothing is linear and nothing is not interactive. Said it the other way. Everything is nonlinear and everything is interactive for the rest of the seminar. Okay. Why? Because we're using categorical dependent variable models. So we don't have the choice here. We're just in this situation. And so we want to talk about how to deal with this. It's already referred to a couple times. The coefficient is going to be, let's just say, not ideal or not that useful. It's a very limited summary of what you're interested in. Okay. There are some ways it's actually problematic, but let's ignore that for a second and say mainly it's just not a very satisfying understanding of what's going on. We can interpret things a couple ways. We can get into multiplicative effects. And so we can say, for that group compared to that group, it's this many times more likely for something to happen, which is a little bit useful, but also has some wonky properties. We'll really talk mostly about how to get into a metric that we care about, get into predictions. Really, I want to get to probabilities. So if I want to know whether a vaccine works or not, I want to know what % of people are protected if they get the vaccine. Well, really, that's a probability. It goes from 0 to 1, or you could think 0 to 100%. No one is protected if they get it. 100% of people are protected. 50%, like the flu vaccine, it's more like 50-50. Still worth getting, especially at the population level, right? If we decrease the prevalence of flu by half in the population, it's still really useful. Okay. But that's really the metric I want to get back in, and actually we're gonna have to do some work. The coefficients aren't cleanly summarizing in that sort of neat metric. Okay, question in the chat. In terms of a nonlinear effect, we're talking about a fixed effect, not the random effect. I am not talking about any random effects at all during this seminar. So yeah, everything is what we call a fixed effect. It's just that normal coefficient, right? When you have a linear regression and you put a continuous and a binary variable in, I'm talking about those coefficients from a sort of typical model. You can expand this stuff to multi-level models to random effects, but I'm not going to cover that. If you're interested, if you're using that in your own work, feel free to ask Slack questions, because I do use multi-level models in my own work, but I'm not assuming any knowledge of them for this class. Okay, so this is one thing that I think is really important to keep in mind. This, it might have been a bigger or smaller emphasis when you learned it, but this. All regressions do is they model means and conditional means. Okay. Fun fact, if you run a linear regression without any coefficients, you're just going to get a constant. That's the mean in the data. Okay. If you run a linear regression for income, but no other variables, you're going to get a number. It's going to be the mean of income. If you then put gender categories in the model, well, it's going to represent the mean of income for different groups, the mean for women, mean for men, mean for non-binary folks. Okay, that's what we're doing. We're just modeling the means. Okay, now for some reason, people lose sight of this fact that we're just simply modeling means when we get to binary data. But if you keep in mind that's what we're doing, I think it will really help you see where you want to go in terms of interpretation. So when we have a 0-1 variable, so a binary variable, I always code my binary variables. Well, 1 means, that thing happens or it has that thing. So if my binary variable is diabetes, I code it as 1 if the person has diabetes and 0 if they don't. Okay. Well, then what's the mean of a binary variable? It's simply the proportion of ones. Okay. If the mean of my diabetes variable is 0.15, that means 15% of the population has diabetes. Okay. That's all it means. It's just simply the proportion in the data that has that thing, has that value of 1. We write this as an expectation. An expectation just means take the mean of y, which could be diabetes prevalence, for example, based on some x's, age, gender, etc., whatever. Example I have here is, think back to like the 538 election example. Let's say we want to know whether someone voted in the last election, and we're trying to describe, was turnout high or low among certain groups. So I'm sort of retrospectively looking at it. In 2020, it was one of the highest turnouts in a long time. 67% of people voted, which is quite high in the US. It's been sort of closer to 50 actually in certain years. So really high voter turnout in 2020, about 2/3 of people voted. So if I had data on all the voters in the US, and I did a summary statistic, I would find the summary is 0.67. That's the mean of the variable. Did you vote or not? What does that simply mean? It means that 67% of people voted. If I want to think about it in a model-based way, what's the probability that any random person voted? Well, there's a 0.67 chance that any random person voted, right? So if I grab from the US population at random, there's a 67% chance they voted in 2020 because 67% of people voted in 2020. Okay. Now here again, I'm not conditioning on anything. I'm just looking at the overall outcome. But usually, if I was doing this analysis, I might be interested in like, did different groups, was turnout higher among Democrats or Republicans, higher among older or younger people, things like that, right? So I want to condition on variables. So here, for example, I could condition on what's the probability that you voted if you're not a Democrat versus if you were a Democrat. This is hypothetical data. I don't actually know the exact numbers of this, but let's imagine that in 2020, 72% of Democrats voted and 62% of non-Democrats voted. Well, conditioning on not being a Democrat, your probability of having voted or being a 1 is 0.62. So the probability that someone who's not a Democrat voted is 62%. The probability that Democrat voted was 72%. Again, I don't know the actual numbers from 2020 here. The 67% is real. That's really the amount voted, but this would be an example. Now, think intuitively. I'm going to give you like 15 seconds to think about it. Okay. If you wanted to see the effect of identifying as a Democrat on voting, okay, and I've calculated these two numbers, 72% of Democrats voted, 62% of those didn't vote. Just think in your head, how would you summarize the effect? What's the effect of being a Democrat on voting? My guess, or at least once I explain it, you'll probably think it's pretty intuitive. I would subtract those two numbers. And I would say Democrats voted at 10 percentage points higher than non-Democrats did. What's the difference between being a Democrat and not? Well, it's a 10% chance in having voted. Simply reflects turnout was a little higher among Democrats. Okay. Now that's actually the marginal effect. The marginal effect of identifying as a Democrat is 0.72 minus 0.62 equals 0.10. But the coefficient is not in that metric. The coefficient is not going to be 0.10. It's doing something completely different. Okay. But to me, this seems clear to me. The sort of cleanest description of the data is these two numbers, and then subtracting them is the effect, is the difference between the groups. It's going to take some work to get there, but I wanted to be clear from the off that that's actually where I want to go.